नमस्कार बच्चों, मेरा नाम धन्या और हम लोग सीख रहे हैं ग्रेड 11 केमिस्ट्री का थर्ड लेसन पीरियोडिक क्लासिफिकेशन ऑफ एलिमेंट्स. Okay, so in the last video, we talked about atomic radius, the different kinds of atomic radius, and the trends in along the period and down the group. Okay, now in today's video, we will be talking about ionization energy. Now, what is ionization energy? Now, in case of atom, we have the positive nucleus and the electrons are moving around the nucleus, and the nucleus is positively charged and the electrons have a negative charge. There is an electrostatic force of attraction. So there is electrostatic force of attraction between the electron and the negative electron and the positive nucleus. Okay, now to remove this electron, in order to remove this electron, we need to provide some energy. Okay, now this energy needed or provided to remove the valence electron. Valence means the electrons from the outer shell. Valence shell electron of an isolated neutral gaseous atom to form gaseous ion. Okay, so the energy needed, so it's the energy needed to remove the valence shell electron of an isolated neutral gaseous atom to form gaseous ion. So isolated because we get isolated in the gaseous form only. Okay, for example, if I have, if it is difficult to remove if they are in the solid state. Okay, so because they are held together, the forces are more. So we get isolated only in the gaseous state, isolated atoms only in the gaseous state. Now, the representation is like this. If there is a metal atom and it is losing electron to form metal ion, okay, and we said energy is needed. Okay, so the energy needed, we write it as delta H. Okay, now this delta H is the energy needed to remove the valence electron of an isolated neutral gaseous atom. Right, now this delta H is called as heat of reaction. Heat of reaction. Okay, and this is the ionization energy. And always this delta H will be positive. This value of delta H will be a positive value because what is happening here? You are providing heat. Okay, energy is needed. Energy is absorbed by the reactant, or energy is absorbed by the atom. So that is why it is delta H is positive, that is, it is endothermic. Okay, so delta H is always endothermic because energy is absorbed. In this case, ionization energy, delta H is always positive because energy is absorbed. It is endothermic. Okay, now coming to the unit. Unit, which is important. Unit is electron volt per atom or kilojoules per mole. Okay, it's an energy term. So electron volt per atom or kilojoules per mole. Okay, and in order to convert the electron volt to joules, you have 1 electron volt is equal to 1.6 times 10 raised to minus 19 joules. Okay, so this is how you convert electron volt to joules. So this is very important. Okay, and also 1 electron volt per atom is equal to 96 kilojoules per mole. Okay, so these are some conversions you need to remember, because questions can be asked from for any conversion. Okay, so please remember this. This is very important. Okay. Now, students, so energy is needed to remove the valence electron shell. Sorry, electrons in the valence shell of an isolated neutral gaseous atom to form gaseous ion. And this energy provided is called the ionization energy, which is positive. Okay, so IE I'm writing as a short form for ionization energy. Okay, let's move on now to something very important from where questions are always asked, and that is the successive ionization energy. Okay, this is very important. So we have successive ionization energy. This is a very important topic. Now, successive. Let's see what it is. If I have a metal atom and I'm providing some energy, electron is removed, and I get a metal ion. Okay, so I get I'm giving energy which is equal to ionization energy 1. This is the first ionization energy. So IE1, first ionization energy. Okay. Similarly, from this metal ion, I want to remove one more electron and I provide energy. It will give me metal 2 plus ion, and the energy that I'm providing is called ionization energy 2, second ionization energy. This is for the second electron. This is for the first electron. Okay. Suppose if I have to remove electron again from this metal 2 plus ion, I provide energy again and I get metal 3 plus ion. And for the third ion, the energy that I'm providing is third ionization energy. So you can see this is a successive ionization energy. Ionization energy 1, 2, and 3. Now, here they usually ask to arrange them in order of increasing or decreasing ionization energy. Which one is higher, or which value of ionization energy is higher, or which one is lower. Okay, so this is one of the important questions. Okay, now suppose in case I have, for the first one, if I have metal M plus ion, right? Over here, the metal M plus ion, I have one electron has been removed. So I have less number of electrons in the outermost shell. So the nuclear charge is more. So nucleus will attract the rest of the electron more strongly. So it's difficult to remove the electrons, right? Because the nuclear charge has increased here. Nuclear charge increases because one electron has been removed, and this attraction of the nucleus to rest, positive nucleus to rest of the electrons increases. So the nuclear charge increases. So it is difficult to remove the electrons. So that means ionization energy 2 is greater than ionization energy 1. More energy is needed to remove an electron from this positive charged ion. Okay, again, if I compare this, the second one and the third one, for example, M2 plus. Here they have lesser number of electrons, here 2 electrons have been removed, so it has less number of electrons. So this attraction of the positive nucleus on these rest of the electron is more. So it is the electrons are, the force of attraction increases more. So you have to provide more energy. So here nuclear charge increases even more. Nuclear charge increases even more compared to our first case. So that means ionization energy, more energy has to be provided. So the third ionization energy is more than second ionization energy. So how can we write the order, how can we write down the order? So that means ionization energy 3 is greater than ionization energy 2 is greater than ionization energy 1. This is always true. This you have to remember. Okay, this is always true. Okay, so the reason what you would write is the reason that you would write here is after losing the first electron, the number of electrons or the number of valence electron, what happens? Decreases. So the pull on each electron increases, okay, and becomes difficult to remove the electrons. Okay, so this is always true. So please remember this case. Okay, so moving on further, so this we will be using, okay. Now the next topic that we are going to do is factors on which ionization energy depends. Okay, so factors on which the ionization energy depends. First one is the atomic size. Okay, so if I have a small atom and I have a big atom, okay, so the electrons of the smaller atom are quite close to the nucleus. They're held more tightly, okay, and more energy is needed to remove the electron. Okay, basically the energy that you're providing, it breaks apart the or reduces the forces of attraction, right? Then in the second case, if the atom is bigger, the valence electron, you can remove the valence electron only, right? Not the inner electron, right? So for a bigger atom, the valence electron is, for in case of B, this is A. In case of B, the atom is bigger, so valence electron is away from the nucleus. So it's easier to remove the electron. So we can say ionization energy is inversely proportional to the size. Okay. So closer the electron, more difficult to remove. Okay. And vice versa. So this is the first case. Now coming to the second factor. So this is easier. Second one is the nuclear charge. Nuclear charge. Okay. Or the effective nuclear charge. Effective nuclear charge. It's nothing but the number of protons. Okay. So if here again, if I take two cases where in the first one, I have A, suppose it has three protons, and there is electron. Okay. So here I just mentioned the valence electron. Okay. Here again, I have maybe 5 protons. Okay. Okay, electron. And more Z value is for which atom A or B. More Z value is for B because there are more number of positive protons. Okay, so more Z value or more effective nuclear charge, more is the ionization energy. Okay, so we can write ionization energy is directly proportional to effective nuclear charge or nuclear charge. Okay, so as the number of protons increases or as the effective nuclear charge increases, the ionization energy increases. Okay. Now, coming to the third one, third factor, which is the electronic configuration, which is very important. Electronic configuration. Now, if the electronic configuration is stable, that means we just, when we were doing the configuration, we learned about half-filled and full-filled shells. Subshells, okay? So if it is half-filled or full-filled, half-filled means what? If it is, P has 6 orbitals, so P3 is half-filled. If D has 10, D5 is half-filled. F has 14, 7 is half-filled. Similarly, if P is fulfilled, D is fulfilled, and F is fulfilled, it becomes difficult to remove the electrons. Okay, so this type of stable configuration will make it more difficult to remove the electrons. So ionization energy is more for these kinds of configurations. For example, if I say D2, sorry, if I say P2, P3, and P5, okay, which one has a stable configuration? Who has a higher ionization energy? It is P3 because it has half-filled shells. Okay. For example, a question is asked, why nitrogen atomic number 7 and oxygen atomic number 8. Nitrogen has a higher ionization energy. So ionization energy for nitrogen is more compared to ionization energy of oxygen. The reason. So you can check the configuration. For nitrogen, it is 1s2, 2s2, 2p, 3. For oxygen, it is 1s2, 1s2, 2s2, 2p4. So who has the half-filled p orbitals? So nitrogen has a stable configuration. So stable half-filled configuration. Stable configuration, why? Because it has half-filled p subshell. Okay, so ionization energy is exceptionally high for these kinds of stable configuration. Okay. Now coming to the next one. Which is subshell effect or penetration effect. Okay, for example, if I take 2s and 2p, okay, it is easy to remove the electron from 2p. Okay, so it is in the order, it is difficult to remove from S. It is difficult to remove from S. Okay, this is the order. It is difficult to remove electrons from S subshell compared to P, D, and F. Because S is very close to the nucleus and also of the spherical shape. Because of the spherical shape, it makes it difficult for electrons to be removed. More energy is needed. And it is easy to remove, less energy is needed, easy to remove from F. Okay, because of that 8-fold shape, and that is why it is easy to remove from the F subshell. That means less energy is needed. So this is the order you must remember. It is difficult to remove from S, then from P, then from D, and then it is easy to remove from F. Okay. So this is the subshell effect or the penetration effect. Now, coming to how does it affect along the period? How does the ionization effect, energy affect along the period and along the group? Variation along the period and in the group. Okay. Now, variation of ionization energy along a period and group. The first one is along a period from left to right. From left to right. Now, suppose I take the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So as you move from left to right, what is happening to the effective nuclear charge? It is increases, right? Increases. So as the nuclear charge increases, the ionization energy is directly proportional. So ionization energy, we learned, is directly proportional to nuclear charge. So ionization energy As you move from left to right, it is increasing. It is increasing. What is the reason? The effective nuclear charge is increasing. Now, this is a general trend. There can be variation that we will be talking about. Okay. First, this is the general trend. Second one is down the group. Okay. So I have the first one, hydrogen and hydrogen, first group, hydrogen, lithium, sodium, potassium, and yeah, this is enough here. So as you're coming down, what is happening to the, as you're coming down, what is happening to the sizes increasing. So size is increasing. As the size increases, the valence electron is far away from the nucleus. So we know that it is easy to remove the electrons as the electron is far away from the nucleus. So ionization energy is inversely proportional to size. So ionization energy, as you're coming down, the ionization energy decreases. So it's easy to remove electrons from potassium compared to sodium. And then easier to remove from sodium compared to lithium, and so on. So this is the general trend. Okay. Coming to some exceptional cases. If I have example, if I have hydrogen and the first period, hydrogen and helium. Okay. It is seen that helium has higher ionization, exceptionally high ionization energy compared to hydrogen. This is one atomic number. This is atomic number 2. Okay. Here, what is happening? Helium has 2 electrons, and both the electrons are in the s subshell. Okay. And it is fully filled. This is fully filled. This subshell is fully filled. Hydrogen has only 1 electron, right? So this fully filled subshell makes it difficult for the electrons to be removed easily. So it has a higher ionization energy. Helium has a higher ionization energy compared to lithium. Okay, so this was for period 1. Now coming to period 2, I have lithium, beryllium, boron. Some discrepancies you will be seeing in some of them. Carbon, nitrogen, oxygen, fluorine, neon. Okay, so the atomic number is 3, 4, 5, 6, 7, 8, and 9, and 10. Okay, so what is the expected ionization energy from left to right? Ionization energy increases, right? That is the general trend, right? Because what is the reason we discuss? Because as Z increases, so ionization energy also increases. This is a general trend. This is the expected. But in reality, okay, let's check out what's happening. So I'll write the configuration in a different color. So I'll just write down the outer electronic configuration. 2s1, so lithium is 3. So 1s2, 2s1. This is 2s2. This is 2s3, 2, sorry, 2p. Two P, two P1. This is 2P2. This is 2P3, 2P4, 2P5, 2P6. Now, here there is a discrepancy case because nitrogen, you can see it's half filled, neon is fully filled. So these two elements have exceptionally high ionization energy, nitrogen and neon. Okay. So in this case, the expected order is this one, right? Lithium has a higher ionization energy than beryllium, boron, and so on. This is the order that is expected. But because nitrogen and neon have half-filled and fully filled subshells, in reality, the order is a bit different. Lithium is less than, this trend is the same, beryllium, then we have carbon, then we have oxygen, then nitrogen, because nitrogen, as discussed earlier also, nitrogen has a higher ionization energy than oxygen because of the half-filled. Okay, then next one will be fluorine, and next one will be neon. Okay, so this is the small discrepancy that is seen. Okay, so these half-filled and fully filled subshells, if they have half-filled or fully filled subshells, these elements display exceptionally high ionization energy. Okay, so the same trend is seen in period 3 also, because in period 3, we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Okay, so here magnesium, the configuration, the last shell configuration 3s2, this is 3p3. Okay, so the actual order, this should be the actual order, right? But in reality, magnesium has a higher ionization energy compared to aluminium because of the fully filled S subshell. So order will be, so whenever you see half filled or fully filled, it will be having exceptionally high. Argon also has fully filled, it is already having a higher ionization energy. Okay. So these discrepancies have to remember. Okay, so fully filled and half filled have exceptionally high. Because of fully filled and half filled subshells, elements have exceptionally high ionization energy. Now, students, variation of ionization energy along the period we discussed. Now, down the group. Okay, if we take an example of group 1, okay, so these are the elements: lithium, sodium, potassium, rubidium, cesium, and francium is there, but because francium is radioactive element, we are not considering that. So as you're coming down, the size increases. So because the size is increasing, size increases. So as you're coming down, the ionization energy decreases down the group. But if you're going up, the ionization energy increases. And cesium has the, if we compare these elements, cesium has the biggest, or the size is bigger, so it has the lowest. Cesium has the lowest. Cesium has the lowest ionization energy. Okay. Similarly, if I take an example of group 2 elements. So I have beryllium, magnesium, calcium, strontium, barium, and radium. If you're coming down the group, similarly, the size increases and the ionization energy decreases, reduces, right? So this was down the group. Now let's take a question, okay? Now we learned about the size, we learned about the charge, nuclear charge, along the period down the group. Now, if we take a question, if suppose they ask you to compare ionization energy, first ionization energy, okay, first ionization energy and the second ionization energy of oxygen and nitrogen. Let's check how does it look like. Okay, oxygen, the atomic number is 8, nitrogen, the atomic number is 7. Okay, so first writing down the electronic configuration. Oxygen is 8, so I have 1s2, 2s2, 2p6. No, it's not 2p6, it is 2p4. Okay, this is oxygen. So oxygen, this is the p subshell. So 1, 2, 3, 4. Okay, now the first ionization energy, it's losing 1 electron. So first ionization energy is O plus. O plus, usually oxygen has a negative charge. Here I have put plus because it's losing an electron, right? So O plus. Okay. When this is O plus ion, and now what is the configuration of O plus? 1s2, 2s2, 2p3. Okay, so 2p3 configuration you must remember because it is half filled. So this is half filled. Here itself we will just mention so that it is easier for us. Now it is losing another electron, okay, and it will form O2 plus. This is ionization energy 2. Okay, 2 plus. So ionization energy 2. This is for oxygen. Now let's check out for here ionization. Obviously, the ionization energy 2 will be more than ionization energy 1 for in case of oxygen, if we just compare for oxygen. Okay. Now let's write for nitrogen and then we will compare both of them. Okay. Now nitrogen is 7. The configuration is 1s2, 2s2, 2p3. So you must remember this configuration, what type of configuration this is. So this is half filled, right? So it's a special configuration which is stable. Okay, special in the way it's stable configuration. So it is losing one electron and it will give you nitrogen plus. These are all anions, but usually they form, mostly they form negative ion, but here I'm writing positive because here it's losing an electron. Okay. Okay, it's losing an electron, fine. This is ionization energy 1. Okay, so now the configuration is 1s2, 2s2, 2p2. Now this is ionization energy 1. Now we need ionization energy 2 also. So it will again lose one more electron. It will give you N2 plus. This is ionization energy 2 needed to remove the second electron. This is 1s2, 2s2, 2p1. Now we have to compare which one is greater. We have to compare between oxygen and nitrogen. So if we see the first ionization energy, if we compare the first ionization energy of nitrogen, because first ionization energy of nitrogen will be greater than the first ionization energy of oxygen. Why? Because nitrogen is half filled. I've already written here half filled, right? Now, if we compare the second ionization energy, which one will be greater? Second ionization energy of oxygen will be greater than second ionization energy of nitrogen. Because after removing, in case of oxygen, after removing the first electron, it becomes half-filled. It has a special configuration of half-filled, stable configuration of half-filled. To remove an electron from the half-filled is very difficult. So from here, removing needs more energy, So that is why the ionization energy, second ionization energy of oxygen is greater. Okay. And in the first case, the first ionization energy in the nitrogen is already half filled. So that is why it will need more energy to remove the first electron. Okay. So I hope this is clear. Right. Now, we will discuss another case. So I hope this is clear. This is very important question. Okay. Usually questions are asked from this part. Okay. Comparing, you must know the reason too. Okay. When we do the past paper questions, it will be more clear that what type the question pattern and health. But if you have another question, compare the ionization energy 1, first ionization energy, and second ionization energy of chromium and manganese. Okay, chromium and manganese. So chromium is 24. Okay, so we will, if it is 24, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But you must remember chromium has a half-filled stable configuration. So that is why there is a small change, 3d5 and 4s1. Okay, so I will not write the whole thing. I'll just write 4s1, 3d5 for chromium. Okay, so always when the electrons are removed, first it will get removed from the S and then from P and then D. In this case, first it will be removed from the S subshell and then from D subshell. Okay, so here there's one electron. Okay, now First ionization energy, so that means it's removing one electron. This is the first ionization energy. Okay, so first the electrons are removed from S. Okay, now because S will be the outer in this case. Okay, usually they write 3d5 4s1 like that. Okay, now here it is chromium plus, okay, and 3d5 4s0. Let's write that 4s0. So one electron is removed. Now it will remove one more electron because they have talked about the second ionization energy also. So this will be ionization energy 2. So chromium 2 plus. Okay, so what will be the configuration now? The electrons will be removed from the d subshell. So 3d4. Okay. Now, in this case, you must see that in this particular case, what kind of configuration this is. D has half filled. So this is half filled. Right? 3d5, it is half filled. Okay. And there's no electrons in 4s. Now coming to the case of manganese, it is 25. Okay. Now, so what will be the change here? It will be 3d5, 4s2. Okay, one more electron, that's it. Okay, so I'm not writing the whole thing. So you just have to add one more electron in S. So that's it. So I'm removing one electron. Okay, so here there are two electrons. So this is the first ionization energy. And here it will become manganese plus this will become 3d5, 4s1. Always the electrons are removed first from the S subshell. Okay. Now just see what kind of configuration this is. In S, it is fully filled. D also, it is half filled. So this is stable configuration, right? So this will be a stable configuration for manganese, right? So, okay, we got manganese ion. Now it is removing one more electron. It will form manganese 2 plus. And this is ionization energy 2. Okay. Now we have to compare the first ionization energies. Okay. In case of manganese, it has a stable configuration. Removing the first electron is very difficult because D is half filled and S is fully filled. So removing becomes difficult. So first ionization energy of manganese will be more than the first ionization energy of chromium. What about the second one? For chromium, after it loses one electron, it gets a configuration in which there is no electron in S subshell, but the D is half filled. So definitely it will be a stable configuration. So removing an electron from this chromium ion will be difficult. So second ionization energy of chromium will be more than the second ionization energy of manganese. Okay. So because here the D5 configuration is very stable. Right. So this type of questions are very common. Okay, students, I hope you understood. So just check the configuration, and if the configuration is stable, ionization energy will be more energy is needed to remove the electron. Okay. Now, moving to another question. You have to compare the ionization energy of ionization energy of nitrogen and N plus. Okay, and nitrogen has an atomic number of 7.
So this, you must remember, keep in mind that both are same element, right? Now, nitrogen, 7. So 1s2, 2s2, 2p, 5. Sorry, 2p3, sorry, 2p3. Okay, now 1, 2, 3. What type of configuration this is? So this is half filled. P subshell is half filled. So it's a stable configuration, half filled. Right. Now, here it will lose one electron and become, when it loses one electron, it is N plus ion, right? And this is ionization energy 1. Okay. Now, what will be the configuration? From p orbitals, it will lose. So 1, 2. It will be 2p2. Now, students, here, if you see, if you lose one more electron from here, this will be ionization energy 2, right? Now, here, nitrogen atom is losing an electron to form nitrogen ion, right? And you get the first ionization energy. Now, here, actually, you don't have to check the configuration because it's the same element. It's the same element. And if for the same element, we learned that the third ionization energy is greater than the second ionization energy, which is greater than the first ionization energy, right? So, in this case, the second ionization energy will be greater than the first ionization energy. So this, when we were learning about this, I said that this is always true. You have to keep this in mind. So if it is the same element, you don't have to derive anything. You can just directly use this rule. Okay. So for nitrogen ion, ionization energy is greater than nitrogen atom. Okay. Now, coming to some exceptions. So this is only for the same element. Okay, if it's the same element. If it's for different element, you do have to check the configuration. Okay, you have to check the configuration for different element. Because it's the same element, you don't have to. Okay, students. Now, coming to some exceptions. Some exception. Now, if I take in some exceptions in the group, okay? So if I'm taking group 13, this is group 13, it's looking like D. Group 13, okay? So boron, aluminium, gallium, IN, tellurium, okay? So as you're coming down, what is happening to the size? Size is increasing. So what is the expectation? Ionization energy should decrease. And the expected ionization energy is boron is greater than aluminium, is greater than gallium, is greater than IN, is greater than tellurium. Okay, this is the expected. But in reality, I'll just explain with a graph. if a graph is drawn between ionization energy and Z, it's like this. We get a W sort of thing, graph. Okay, and this is B, this is aluminium, this is Ga, gallium, indium, and we have tellurium. Okay, so in reality, from the graph, boron is greater than tellurium. Okay, so boron is greater than tellurium. Okay, tellurium will be around here. Oh. So around here. Okay, then again is greater than gallium, greater than aluminium. This is the graph, this is the values we get. Okay, so you can remember the numbers like this. So 1, 2, 3, 4, 5. So just remember the number 1, 5, 3, 2, 4. So just 1, 5, 3, 2, 4. If you remember this, it is easy to write down the order. Okay, I'll just explain the reason. I'll just explain the reason. What is the reason for this discrepancy? Okay. Now, this discrepancy happens because now tellurium has a high ionization energy. It should have a low ionization energy, but tellurium has a high ionization energy. Now, this tellurium comes immediately after the lanthanide. Okay, so if it comes after the lanthanides, that means we have already learned immediately. If it comes after the lanthanide, it will also feel the effect of the lanthanide contraction. Lanthanide contraction is affecting tellurium. Okay, so because the lanthanide contraction is affecting tellurium, the size has become smaller. If it is smaller, if the size is small, what is happening to the ionization energy? Ionization energy increases. So removing the electrons becomes difficult. Okay, so this is the reason for a different behavior of tellurium. So tellurium comes immediately after the lanthanide elements. So it has the effect of this lanthanide contraction. It gets the effect of lanthanide contraction. The size becomes smaller. Okay, so the ionization energy increases. Okay, now gallium. Gallium shows this different behavior because of something called transition contraction. Now, gallium has a poor shielding effect of D subshells, because of which it will show transitional contraction. What is the reason? Because of the poor shielding effect of D orbitals. Okay, so this was the discrepancy for tellurium and gallium. Okay, so just remember this number. It will be easy to know the order. Okay, I hope this is clear. Now, coming to another group. Coming to another group, which is group 4. Group 4. Okay, we have carbon, silicon, germanium, tin, lead. So let's start with the expected one. As you're coming down, what is happening to the size? Size is increasing. So size increasing, and our ionization energy decreases as you're coming down, okay, down the group. So what is the expected order? The expected order is ionization energy of carbon is greater than silicon, is greater than germanium, is greater than tin, is greater than lead. This is our expected order. But in reality, there is one discrepancy. There's one change, okay? Carbon is greater than silicon, is greater than germanium, is greater than lead, is greater than tin. There's only one change here. Now, the reason is because of lanthanide contraction. Lanthanide contraction. Because of lanthanide contraction, the size of lead is becoming smaller. The size of lead is becoming smaller. So if the size is small, what happens to the ionization energy? Ionization energy will be more. So this is for group 4, this is the only discrepancy. This is the only change. Okay. So the reason is because of the lanthanide contraction, because of the small size of lead compared to tin. Okay. Okay, students. Now, the next topic that we are going to discuss is how metallic and non-metallic character, they depend on the ionization energy. Okay, now we have along a period, okay, and down a group. Okay, as we move towards the right, on the left-hand side, we get the metals, and on the right-hand side, we get the non-metals. So non-metallic character is increasing towards the right. Okay. And similarly, down the group, what is increasing? Metallic character is increasing. Okay. So down the group, metallic character increases down the group. Right. Now, for metals, okay, it's easier to remove the electrons. Okay, so since it's easier to remove the electrons, the ionization energy for metals, the ionization energy is less. And if it is less, that means easy to remove electrons, right? If you see, if you come down the group, the size is increasing, right? And what's happening to the ability to remove the electrons? It is increasing. Okay, so less ionization energy. Similarly, for metals, it is easy to remove the metal tend to release electrons. So definitely the ionization energy will be less. So it's easy to remove the electrons. Okay, so that means this is a hint. If the ionization energy is less, then that is a metal. So the opposite happens for non-metals. For if the ionization energy is high, then difficult to remove the electrons. Okay, and that means it shows what characteristics? non-metallic characteristic. So it's a non-metal. Okay, so if we check this periodic table, in this periodic table, from left to right, non-metallic character is increasing, metallic character is decreasing. So here, metallic character decreases. So ionization energy increases. It becomes more tougher to remove the electrons. Now, down the group, metallic character increases. So ionization energy increases down the group. Okay, I hope till here it is clear. So we can present it this way also. Ionization energy, if it is less, that means metallic character is more. So less ionization energy, metallic character. Okay. And also, if it's a metal, we have to talk about metallic oxide. Metal oxides are basic in nature. Basic in nature. Okay. For example, sodium oxide, potassium oxide, all these are basic in nature. Metal oxides are basic in nature. Okay. So, along the period, if we go, okay, from left to right. So from left to right, what is happening to the metallic character? Metallic character is decreasing. So what happens to the basic character? Basic character also reduces. Basic character reduces along the group. Basic character decreases as metallic character reduces. It's changing into non-metals, right? As metallic character reduces. Down the group, what's happening? Down the group, what's happening? Basic character increases because metallic character is increasing down the group. More metallic elements are down. Okay, so this was about the metal. Okay, so metallic oxides are basic in nature. From left to right, basic character reduces. From down the group, basic character increases because the metallic character is increasing. Okay. Similarly, if we talk about non-metals, then it's some opposite. If we talk about non-metal, non-metal oxides are, it will be acidic, the opposite. Right? So that means from left to right in the periodic table, what is happening to the acidic character? Acidic character increases because towards the right, we get more of the non-metals. Towards the right, we get most of the non-metal. Acidic character increases. But if we talk about down the group, what is happening to the acidic character? Acidic nature or acidic character decreases down the group. Why? Because down the group, we get most of the metals. Okay, so let's summarize this about the ionization energy and the basic and acidic character. So we have, if ionization energy is less, metallic character metallic nature is more. If metallic nature is more, what is the basic nature? Basic nature increases, right? If ionization energy is more, that means non-metal nature is more. That means what kind of oxides they are. Acidic, acidity is high. Okay, so if we talk about, maybe just as an example, maybe if we talk about lithium oxide, sodium oxide, and potassium oxide. So arrange in order of basic nature. So we have lithium, we have sodium, we have potassium. So down the group, what is happening to the metallic nature is increases. So basic character, basic nature increases. So basic nature increases. So we have K2O is more basic than sodium oxide, is more basic than lithium oxide. Okay. Okay, students. So in this video, we discussed about the ionization energy. What is ionization energy? How it is affecting along the group, and how it is affecting the different elements along the group and down the period and down the group. Okay, students, that's all for today. Thank you. Have a great day.